Hello, and welcome to week one, where we begin to talk about mathematical tools. The first thing you need to understand about this particular week is these are tools. Tools can be used well or they can be used poorly, and math can be used in a similar way. So, I'm going to try to show you how to use these mathematical tools well. Now, remember, sometimes you do forget, so give yourself some grace along the way. All right, so first of all, scientists measure things. There's lots of ways you can measure things. You can measure things like wind speed, and to measure wind speed, you got lots of different things. My dad is a pilot, and he measures wind speed in knots. You can also measure wind speed in miles per hour. You can measure all sorts of different things. You can measure the power of an earthquake. There are two different scales for that. The one we're more familiar with is a Richter scale. There's another one that involves amount of damage. Richter is how much things shake. There's a scale based on damage. You can measure distances traveled. If you're a human, we like to think of miles, we like to think of kilometers, but if you're a snail, it might be nice to not think along miles and kilometers, but along the order of something called a meter. Now, we can also look at heat, and heat is measured in lots of ways. It is measured in terms of something called a calorie or something called a joule. Heat is different than temperature. Temperature we can measure in degrees Fahrenheit, degrees C, or something called Kelvin, which is an absolute temperature scale. So we measure things, and we got to keep up with these things that we measure, and there's all sorts of ways to do this. Now, the mathematical tools that we're going to be looking at involve how do you convert something, for instance, from miles to kilometers, or from kilometers to miles. So, we need to also understand that not all numbers are the same. Roger Maris hit 61 home runs in 1961. 61, this is an absolute measure. You can't hit half a home run. Two doubles does not equal a home run. It's not the way it works. You can't hit 61.2 home runs. You just hit 61 home runs. Shoe size could be an 8 to an 8.5. If we're looking at pant sizes, we could be looking at something in terms of women's pant sizes of a 12 or a 13. 12 for one brand is different than 12 for another. So sometimes these numbers don't mean much. So this absolute measure, this exact number of 61 is pretty awesome. A shoe size is a measured number, and measurements come in lots of different forms. Again, I will come back to say when we're looking at pant sizes, a 12 at Walmart is not the same as a 12 at the Gap. They are very different than one another. So, while we might be able to categorize the length of a home run, where we can measure it, it's still not the same as just a home run. And so we got to pay attention to how these numbers play out in terms of whether they are exact or whether they are measured. The metric system, or otherwise known as the international system, is something that everyone in the world uses except for the U.S. The U.S., we use the standard system, or the SI system. The international standard of length is the meter. Actually, it's the kilometer. 1 meter, as you may remember from your previous schooling, is 100 centimeters. Remember, centi means 100. So if you divide a meter into 100 parts, you have a centimeter. If you take a meter and you multiply it by 1,000, you end up having a kilometer. So 1,000 meters is equal to 1 kilometer or kilometer. The beauty of this metric system is if you need a larger or smaller unit, you just add a prefix. So if it's smaller, you put centi. If it's larger, you do kilo. This allows us kind of a standard way of looking at things. Now, when we look at really, really small things, we can look at, I already mentioned a centimeter, right? 100 centimeters is equal to 1 meter. When we look at something even smaller than a centimeter, what we find is 1 centimeter is equal to 10 millimeters. So that means we can begin to relate this meter to a millimeter. So if we have 10 millimeters in 1 centimeter, then what we can do is we can say, okay, here's my 10 millimeters. I know I have that in per 1 centimeter, right? So now then I can start to figure out how to convert this into something that's more useful. We can begin to have conversion factors. If we go really small, then what we can use is something called a micrometer or a micrometer. A micrometer is very small. It is dividing 1 meter into 1 million pieces. So a micrometer is incredibly small. Now, as this plays out, we can also look at different types of units. So the size thing is that prefix. So if you go kilo, it's 1,000 times bigger. If you go milli, it's 1,000 times smaller. We can do the same thing with a unit of mass. Mass is a measure of the quantity of matter, not weight. So this is quantity, not weight. How much mass does something have is not a weight measure. So mass is measured in terms of grams. And 1 gram is about 1/28th of an ounce. So if you have 15 grams, you have half an ounce. If you have 30 grams, you have a full ounce, thereabouts. 1 kilogram is equal to 1,000 grams. And 1,000 grams is equal to 2.2 pounds. So this is kind of an interesting thing. So let's say, for instance, we have someone who weighs, and this happened to me. I went to China and was trying to talk about these different things. And in China, one of the interesting things about weight is sometimes, and especially with little children, this is who asked me, a child in about 3rd grade, asked me, Dr. Cabot, how much do you weigh? And so I told them. But to tell them in pounds doesn't work very well. So you got to tell them in something they understand. And because the U.S. uses pounds, so this here is an SI thing, which is USA only. Boy, I have to convert to these kilograms. So let me do something that is pretty easy on the math. So let's say we have someone who weighs 220 pounds. So we need to convert this for that little Chinese boy who asked me, how much did it weigh? We need to convert this into something they will understand of kilograms. So what we do is we set up a conversion. So what we're trying to do is we need to make sure that these pounds go away. So remember, pounds, we could say this as over 1, right? So pounds is in the numerator. So if I can put a pounds in the denominator, then all of a sudden what happens is we can cancel our pounds, right? And we can cancel our pounds by going ahead and saying, okay, well, how many pounds do we have per kilogram? We'll get this thing to working again. It's always wonderful whenever electronics work, and then sometimes they forget to. That's what happened here, so forgive. So we need to convert this into kilograms. So we know that 2.2 pounds is equal to 1 kilogram. So we can take 220 pounds, multiply it by a conversion factor of 1 kilogram per 2.2 pounds. The pounds cancel, right? They gone, and we're left with kilograms. 220 divided by 2.2 is equal to 100 kilograms. So now then we can convert something into another unit of measure. This is pretty important. Now, for small masses, well, you have to use something different. So for small masses, we'll use grams. If that same person who weighed if that same person who weighed 100 kilograms, if we were to take that and convert that into grams, then remember, we got to get rid of the kilograms, right? So how do we get rid of these kilograms? We put kilograms right here, and we got to put grams up here. So now then the kilograms are going to go away, and we know that there are 1,000 because by definition, kilo means 1,000, whatever the unit is, so it's 1,000 grams. So now then, whenever I look at this, I have a measure of 100,000 grams. To try to measure a wonderful person and say that they weigh 100,000 grams, boy, that's hard to figure out and to mentally process. So we have to use units that are appropriate for what we're measuring. In biochemistry, where we're looking at enzymatic function and enzymes and how they work, we'll sometimes use milligrams or even micrograms. Milli is where you divide by 1,000, so you take the number of grams and you reduce it into 1,000 different parts. And with the microgram, you reduce it into that gram into 1,000,000 different parts. So there's some masses for you. You can also measure time. Time is something that Einstein would argue doesn't exist. It's a figment of our imagination, but yet time is. So time we can measure in seconds, we can measure in minutes, we can measure in hours, we can measure in days, we can measure in years, we can measure in centuries, we can measure in eon, millennia, all these kinds of things. Or we could measure things in terms of milliseconds or microseconds. Do you remember whenever you were younger and you would work those digital stopwatches as quickly as you could to see how quickly you could click? That time that you would get where it would say 12, 13, 14, that's the passage of a millisecond. So that's 12 or 13 or 14 milliseconds. That's how quick that reaction is, that reflex is to get that particular time. And so again, with these milliseconds, if we're looking at something that is 12 milliseconds, we can convert that, multiply it by 1,000 milliseconds per 1 second, and we end up with something that is 0.012 seconds. So we can convert things into all sorts of different measures. And this is pretty fascinating to see how this plays out. Now, not only can you measure in time, but you can measure in volume. In the U.S., we like fluid ounces. But the rest of the world works in terms of liters. Now, the reason why liters is based on the volume of water. So if we take 1 centimeter cubed of water, of H2O, what we have is this 1 centimeter cubed of water is equal to something called 1 milliliter. 1 milliliter, when we multiply it by 1,000, we can find that 1,000 milliliters is equal to 1 liter. Now, interestingly, this centimeter cubed, you may know this more as cc's. So when we're measuring volume, sometimes we measure in terms of cc's. When you're getting a shot, you get a shot that's filled with 1 cc. That's 1 milliliter. I was reading a thing the other day, and they said that they needed to do, or I was watching a show the other day, and they said that they needed to give a 20 cc shot. 20 milliliters, that's a lot of fluid. And you can't really do that very easily. So they use IVs to deliver such things, otherwise known as intravenous delivery. And so this becomes an important thing. Whenever you're looking at embalming a body, we're going to be measuring in terms of either milliliters, depending on what we're using, or we'll be using liters in terms of much more embalming fluids, higher level embalming fluids. So there's you some volume. It's measured in terms of liters, which is based on that centimeter cubed of water, that cc, which is kind of nice. So there's our, we rarely ever go to kiloliters. We look at liters as something that is kind of a standard measure. Now, there's this thing called a factor label method. And that is where we can have our units work for us. This is where we start dealing with the tool. So you can cancel those units until you have the correct unit that you should have in your answer. That's what I was talking about in terms of going from 220 pounds, getting rid of the pounds. Remember, you're putting the pounds in the denominator, so you get rid of it in the numerator. Converting it to kilograms. We know 1 kilogram is 2.2 pounds, which gives us 100 kilograms. This is that factor label method that we already talked about. This is pretty important. It's very, very useful. Now, that's one tool. Another tool that's really handy is scientific notation. Most of the time, whenever I'm talking about it, you'll hear me talk about it as scientific notation, not exponential notation. There's a really simple way of doing this. All it is you're trying to take something that is a really big or a really small number and get it to something that we can use. So I have small children. I have a 9-year-old, a 6-year-old, and a 3-year-old currently. And what they like to do whenever they're doing math is they like to use the hands. And with their hands, they have 10 fingers. So this goes all the way back to our inherent ability when we're really young to count with our fingers. So ultimately, we don't want to deal with a big, massive trillion-dollar national debt, because how do we fathom what $1 trillion is? Well, here's 1,000. That's hard for me. Here's 100,000. That's going to take a while for me. Here's 1 million. Or let me back this up. Excuse me. There's 1,000, and then here's 1 million. So that's going to take me a long while to get to. Here's 1 billion, which I'll likely never get to, and here's 1 trillion. Well, you see how it plays out. I can't count there with 10 fingers. But what I can do is something a little different. So what I want you to notice here is this. It's really much simpler to write this as 1 times 10 to the 12th. Now, I want you to count the zeros, okay? So when we go and we start counting zeros, we have 3, and then another 3, and another 3, and another 3. So 3 plus 3 plus 3 plus 3 is equal to what? 12. You see that? So what we do is we count all the things up to this very last digit. If this very last digit falls into our 10-finger range, obviously you can't do 10.1 fingers, that's awkward. So you can do 9.9 fingers and, just hold one up a little bit shorter, but you can't have an extra finger, so you can't do 10.1. So we go to that 1 at the very end and we write that 1, and then we do times 10 to the whatever, and the whatever right here is the number of places that you have between the decimal point right here and that special number, in this case 12. So $1 trillion is $1 times 10 to the 12th. I understand what $1 is. I don't understand what 10 to the 12th is very easily. But whenever I have $1 at 10 to the 12th, and I look at an increase in the national debt by tomorrow of 2 trillion, now then I can see that national debt, if I avoid looking at all these things because those are identical, doubled. It's easier to begin to think through. So that's how large numbers work. Small numbers are even easier. Let me show you how that works. So if I have a small number, so I'm going to say 10 to the negative 7th. So that's where we're at right here, okay? 10 to the negative 7th. So 10 to the negative 7th is 0.0000007. That's really hard to understand. It doesn't make a whole lot of sense to my brain. I understand 1 or 7, but I don't understand 0.0000007. So how would I work this one? Well, in this case, we start to count backwards, okay? So if I look at this, in order to move that decimal point, all you do for this thing is I want you to count the zeros. Now, the zeros that I want you to count are the leading zeros, the ones in the front. So if we count these, the leading zeros here, there are 7 leading zeros, okay? So with those 7 leading zeros, now then, what we do is we say, okay, we got to move that decimal place, but that decimal place moves smaller, doesn't it? So instead of 10 to the positive 7th, we're going to have 10 to the negative 7th because we're getting smaller, okay, smaller than 1. And so now then we write this number right here. So it becomes 7 times 10 to the negative 7th. And it becomes something that we can work with. So we can look at all sorts of different things. So for instance, we can look at, let's say 1, 2, 3, 4, 5, 6. 123,456. If we want to come back and look at this in a different way, we need to put this in the order of our fingers. So we need to get it to 1.23456. Now then we need to count how many places we've got to move to get to that 1. And when we look at this thing, we have 3 here, we have 2 here. 2 plus 3 is equal to 5, so it's times 10 to the 5th. If we were to look at something that is much more weird, how about 0.00218? Just off the top of my head. If I need to convert this thing, then what you do is you take this number here and you make it 2.18, and then you count those leading zeros, right? There are 3 of them, but we're smaller than 1, so we put a negative sign there. So that becomes 2.18 times 10 to the negative 3. Now, if we're wanting to do some quick math to understand some things, and we need to be able to multiply these weird numbers in scientific notation, then it's something that's fairly straightforward. So in this case, using this right here, I'm going to say, well, if I have 10 to the negative 7th, and I'm going to multiply it by 10 to the negative 7th, all we do is we take negative 7 plus negative 7, and that becomes equal to 10 to the negative 14th. Where that comes in handy, this right here, is with something called pH, or measuring acidity of something. So this becomes pretty handy to be able to multiply and divide. Remember, multiplying, we're going to add the exponents. Dividing is a form of subtraction. So here we're going to subtract our exponents one from another. So if we take negative 7, 10 to the negative 7th divided by 10 to the negative 7th, then we have negative 7 minus a negative 7, and we get 0. So it's kind of an interesting thing. Now, in terms of algebra, as a quick refresher on some algebra, we use it a lot, but the fancy word intimidates us. So let's think about this. We think about all sorts of different things. Let's say to get to West Memphis, which is on the other side of the river from Memphis, let's say that to West Memphis, let's call that 210 miles away from where I live. So if I travel at 70 miles an hour, how long is it going to get us there? So remember, 70 miles per hour is an interesting thing. So we can write this as 70 miles per 1 hour, or we can flip it. So we can write something like this. 1 hour, in 1 hour we can travel 70 miles, right? So if I have 210 miles to get to Arkansas from where I live, remember, I've got to use that unit factoring, that tool that we were talking about earlier. I need to get rid of miles, right? And to get rid of miles, I need to put miles in the denominator like this. So then that's 70 miles, 1 hour. 210 divided by 70 is equal to 3 hours. So it's going to take me 3 hours to get to West Memphis. We use this kind of algebra all the time. To determine unit cost, we'll use algebra to figure out things. So when we go through and we start working on some of these mathematical tools, what I want you to realize is they are tools. They are not intimidators. So use the tools to your advantage. Don't let the tools use you. Don't think about them as something that uses you. Use the tools to your advantage. And then things like scientific notation, where we're starting to think about it in terms of number of fingers. We can do that kind of math pretty easily. Or we start thinking about things like conversions of miles to time. We can do that as well. So remember this and you'll go far.